Okay, so last lecture we looked at the transient response with a step input. In this lecture, let us look at the transient response with a sinusoidal input, both small and large amplitudes. So first let us do a quick analysis, and we'll use the same numbers as last time, the same VTs and mu's and everything, DC voltages, and the DC drain current 1 milliamp, the DC output voltage 1.5 volts, GM, RO, etc. The gain is minus 100. Now let us do a small signal high frequency analysis for a sinusoidal input. So we had derived this transfer function last time for this circuit, minus GMP RO, which is again divided by 1 plus S CLRO. CLRO is the time constant. GMPRO is 100, CLRO is 10 microseconds, and we want to convert this to frequency. So 1 by 10 microsecond is 10 raised to 5 radians per second, which is about 16 kilohertz. So if we write VO in terms and the transfer function in terms of JF, where F is the frequency, so you'll get minus 100 divided by 1 plus JF divided by 16 kilohertz. Gain bandwidth product of this transfer function is 100 times 16K, which is 1.6 megahertz. Okay, let us do a little more calculation. Let us say we've applied a sinusoidal input to our circuit, and this is the sinusoidal output. So the output goes from the DC value, for our case 1.5 volts, to 1.5 plus the amplitude of the sinusoidal signal. Now if the frequency of the signal is F, then the time period is capital T. Then in T by 4, the output must go from its DC value to DC value plus Vm. And that, so if we do some let us do some calculations. So the current that must flow is ID C dV dt, and for the sake of approximation, let us replace this sinusoid with a straight line, so that we can write this as delta V by delta T times CL. And our ID SAT, as we saw last time, is 1 milliampere. So 1 milliampere is available to cause this charging of the capacitor or discharging. CL was 1 nanofarad. Let us assume that the delta VO, this capital VM, is 1 volt. Then and delta T of course is T by 4, which is 1 by 4F. So we put all of this together, then we get 1 milliamp equal to 1 nanofarad into 1 volt divided by capital T by 4. And that is equal to, so T is 1 by F, so we get 4F nano. Alright, this comes out to be 4F, where F is the frequency, which gives us, so if I find F from here, to be 250 kilohertz. What this is telling us is that with a 1 milliamp current available, this circuit will charge to 1 volt, a change of 1 volt, well enough up to 250 kilohertz. Alright, so if the frequency is greater than 250 kilohertz, then the charging will not be, the charging with a 1 milliamp current will not be sufficient. Alright, now we just saw, so let's go back. So the 3 dB frequency of our circuit is 16 kilohertz. This calculation shows that the circuit will charge properly up to 250 kilohertz. So if you want to see the effect of slewing, then we must operate this circuit at greater than 250 kilohertz. But with a 3 dB frequency of 16 kilohertz, at 250 kilohertz, the gain of the circuit would have dropped significantly, and we will not see the slewing effect. So to observe the slewing effect, it is most effective if we put this circuit in a unity gain feedback, because with unity gain feedback, the 3 dB frequency will become 16 megahertz, the gain bandwidth product, and 16 mega is greater than 250 kilo. So we'll see a nice slowing effect in a unity gain configuration. In fact, this also tells us, what these numbers tell us is that often slewing becomes a problem for amplifiers when they are put in unity gain feedback, so that the gain is smaller but the gain bandwidth product, I'm sorry, the bandwidth is larger, and then slewing becomes more of importance or worry, whichever way one looks at it. Alright, so having said all that, we have an amplifier that is a single input amplifier, but it is not possible to put an amplifier unity gain if it is a single input amplifier. So we need to build a double input, 2 input amplifier from our circuit. So the best thing, simplest thing we'll do is we'll just build a differential amplifier with our same numbers that we used for M1, M3. We do M2, M4 and build a differential amplifier and put this in a unity gain feedback configuration, which is this. If we short the gate and drain of M2, this is a unity gain feedback differential amplifier. Now, first, whenever we do this, it is a good idea to check the DC characteristics to make sure to see what they look like before applying transients. It's a kind of it's a good habit for any circuit you build. So whenever you do any feedback, do a DC transfer characteristics before doing transient or frequency response. Now we can do this on paper, and I'm leaving that to you as homework to do this analysis on paper, or specifically find the VO max and VO min of this circuit in unity gain. We did this for 3 different configurations earlier, but we have not done it for this specific one. So you do it as homework. I'm going to do it in Spice because it is a very nice picture. It's very instructive to do this. So here is the circuit, 5 transistors, VDD. The gate voltages are applied. By the way, VG5 is slightly different from 0.6 because of channel length modulation. So now we'll do our DC transfer characteristics and just plot the output voltage, which is VO. So I'm plotting VO for this circuit. Alright, so let us look at this VO. So in fact, for a unity gain amplifier, when the input goes from 0 to 3, ideally we would like the output also to go from 0 to 3 with a slope of 1. Alright, but what we are seeing here is something completely different. So the output is constant at about 0.67 volts until the input crosses 0.5 volts, nearly 0.5 volts. So why is that? For below 0.5, the input transistors are actually off and no current flows. I'm sorry, not the input transistor, the M1. So let's go back and look at M1. So we are changing this V in and we are looking at this VO. So as long as V in is small, for less than 0.4, M1 is off and it carries no current. And so change in V in has no effect on the output voltage. So the output is constant at some value. So that is what this is showing. The output is constant up to the input crossing some threshold. Then it is rising, and here it is kind of linear. So this is the region in which the amplifier works as a unity gain circuit. Then above 1.2 volts, again the output is saturating to about 1.15 volts. So the output voltage range is only about 0.7, 0.67 to about 1.1 volts, a very small output voltage swing. Alright, so this is, in fact, this is similar, if you recall, to the telescopic cascade differential amplifier. So this does not make a good closed loop configuration. For our purposes, it does not provide an enough input range. So So the input range is very small. It is the same as the output range, is only 0.2 volts. So we will not be able to see a nice slew rate behavior with this circuit. So what we need to do is build a differential amplifier from our amplifier, and what we do is this: we introduce a unity gain differential amplifier before our common source amplifier to make it two inputs, and this we'll treat as ideal. So this is an ideal amplifier which has two inputs and an output, and the output is simply equal to the difference between the two inputs with a gain of 1. This is not a realistic circuit because we are assuming this to be an ideal amplifier. It is not realistic, but it very nicely demonstrates the effect of slew rate. So let us look at this circuit. So what I have done is I have put a unity gain feedback. So the output is connected to actually the positive input, because this plus minus refers only to this amplifier at the output of which is connected a common source. So from VO1 to VO there is an inversion. So with respect to this as an input, the output is negative, and so we connect the negative to this back, and now we apply our input here. So for this amplifier, only this is the equation. Now note that at VO1 we need a DC voltage of 2.4 volts to bias MP in saturation. So that will have to be supplied in when we do the analysis of this circuit. So that's why I said this is not a realistic circuit, but it gives very nice it shows very nicely the effect of slew rate. So let us look at this circuit. So this is a circuit, M and MP, the gate voltages. So there is a 2.4 volt DC, and the E1, a voltage dependent voltage source, basically simulates the ideal amplifier. Oh, I'm sorry, this should be 1, not 100. Okay, so the gain is 1. Now let's do a DC analysis first. So it's already put in a closed loop configuration, and let us do a DC analysis first. So the AC is also not needed, and so let's run this and look at the output voltage VO. Okay, so the output voltage as the input goes from 0 to 3, now the output also is nicely going from 0 to 3, almost. There is a small 0.1 volt which will stay to keep the so here MN and here MP on. Alright, so there is a slight bending over, but otherwise this is almost an ideal unity gain feedback amplifier. Now let us apply a sinusoidal signal to this. So we'll do a transient analysis and comment out the DC. And let us start by, so I'm applying a sinusoidal signal with a DC offset of 1.5. No, why is this 1.5? This should, yeah, okay. So why is this DC? Well, I should explain what is this. Okay, so at the input, so if the output we saw earlier, the DC output voltage of this circuit is 1.5 volts. Alright, so in this configuration also this voltage has a DC of 1.5 volt. So we apply a DC of 1.5 at the input, and on top of it we'll ride a sinusoidal signal. So there's a DC of 1.5 on top of which rides a sinusoidal. So I've put a frequency of 300 kilohertz, which is greater than 250 but less than 1.6 megahertz. So 300 milli is the input amplitude, and let us run it now. So let's see what this does. Alright, so okay, so this is the output. Let us also plot the input to compare. This is a unity gain, so the input should be equal to the output if the circuit behaves linearly. So this is input. Alright, so the red is the input, the blue is the output. They are basically identical. The output is slightly shifted to the right compared to the input. Why is that? Why is there a slight shift? The shift is because at 300 kilohertz there is a slight phase shift between the input and the output. If you look at the transfer function and find the phase shift, you'll find that there is a small phase shift which causes the output to be shifted, but the shape is the same. The shape is identical, almost identical, which is good enough for us. There is a slight decrease here, but we'll ignore that decrease. That slight decrease is also because of that the 300K is not too far from the 3 dB frequency of 1.6 megahertz. All right, let us increase the amplitude to 1000 milli or 1 volt. All right, 1000 millis, which is 1 volt. All right, now let us run it and see. Okay, so now the blue is the output. Now we can nicely see the effect of slew rate. All right, so what is happening is that the capacitor has to discharge. The output is going lower from its DC value. So the capacitor has to discharge through Mn, and Mn provides only 1 milliamp of current, and the 1 milliamp at 300 kilohertz is not large enough to discharge the capacitor in time, and so the output voltage is slewing. It is discharging not sinusoidally but linearly, because now the rate of change of the output voltage is limited by 1 milliamp, and therefore the output goes slower and does not follow the input signal. All right, this is slewing. This is the slew rate effect on the output voltage. And if we make it even higher, let us try 1200, you will see the effect even larger. All right, so that you can see more prominent, the slewing is causing more delays and more distortion in the output signal. All right, so okay, so let us draw a conclusion. Okay, let me just read this out. So while the small signal bandwidth of a circuit may suggest a fast time domain response, the large signal speed may be limited by the slew rate, because the current available to charge and discharge the dominant capacitor on the circuit is small. So we saw that for 300 millivolt input, the output followed the input faithfully, and that was predicted by the small signal bandwidth. But for large signals, the speed was limited by the slew rate. So if the signal is large, then the circuit cannot be operated at 300 kilohertz, even though it has a unity gain bandwidth of 1.6 megahertz. All right. Moreover, since the input-output relationship during slewing is non-linear, as we just saw, so this is not linear at all. All right. Therefore, the output of a slewing amplifier exhibits distortion. Because what is happening is that the output is not following a sinusoidal signal, it is linear, and that causes distortion. To avoid distortion, if a circuit has to amplify a sinusoid Vm sin omega 02, it must have a slew rate that exceeds V0 omega 0. All right, you must, where V0 is the output amplitude. All right, Vm is the input amplitude, V0 is the output amplitude. You should kind of convince yourself that this statement is true. All right, so it's a short lecture. Next lecture, we'll look at the calculating the slew rate of various op-amp configurations. So the chapter 9 op-amp configurations that we've studied, now we'll calculate the slew rates for some of these op-amp configurations.